This is Jack Jackson again, and in this video we're going to continue to prove some of the properties that we have of limits, these laws of limits. In this particular one we're going to start with trying to prove limit property 4. Let's go back and look here. Remember we had several properties of limits, and here we did. We proved a couple of these in the last video. Actually proved the first 3. So remember, the hypothesis here was that the following limits exist. That the limit as x approaches c of f of x equals some real number limit L, and the limit as x approaches c of g of x equals a real number m. And the proof we're going to do is we're going to let c be a particular real number, but it's actually also true when c is infinity or minus infinity. But remember, L and m are not infinity or minus infinity. They're actual real numbers. Okay? And we're going to prove that the limit of the product is the product of the limits. Seems reasonable, right? Let's see if we can actually prove it. Okay. So we're going to be make use of the formal definition of a limit using absolute value on this one. So a lot of times I've been using a slightly different form, but we're going to use this form. For real numbers c and L and a function f, we say the limit as x approaches c of f of x equals L if and only if for every real number epsilon greater than 0, there exists a real number delta greater than 0, such that if 0 is less than absolute value of x minus c, which is less than delta, then f of x minus L, take the absolute value, is less than epsilon. So that's the way to phrase those inequalities in terms of absolute values. And we're also going to make use of the triangle inequality. This is an important property with numbers. For any real numbers a and b, the absolute value of a plus b is always less than or equal to the absolute value of a plus the absolute value of b. In fact, if a and b have the same sign, you get equals here. The absolute value of a plus b is absolute value of a plus absolute value of b. But if they have opposite signs, one's positive, one's negative, then you get something smaller on the left than you do on the right. So that it's strictly a less than. All right, so here we go. Suppose we are given that the limit of x as x approaches c of f of x equals L, and the limit as x approaches c of g of x equals m. Then that's the hypothesis. Now, suppose we're given any value of epsilon greater than 0. So let's look at a new number, epsilon 1. Epsilon 1 is going to be epsilon, original epsilon, divided by 2 times 1 plus the absolute value of m. Since I've got absolute value here, this is at least 0 or bigger. Add 1, this is at least 1. Times 2 makes the bottom a positive number. Divide it into a positive number, you get a positive number. So this is our new epsilon. And for this epsilon 1, since the limit of f is L, by definition there's a corresponding to this epsilon 1, there's a delta 1, which is positive, such that if the absolute value of x minus c is between 0 and delta 1, then the absolute value of x minus L is less than epsilon 1, which is this expression. Similarly, there's an epsilon 2 that is epsilon over 2 times 1 plus absolute value of L, which is also a positive number. And since the limit of g is m, by definition there's a delta 2, which is positive, such that if x is close to c, absolute value of x minus c is between 0 and delta 2, then g of x minus m is less than epsilon 2, which is this one here. Notice that the epsilon 1 has something to do with the limit of g, and that's the one I applied to L here. And the one that has to do with the limit of the L here, which this is the limit of f, I use that to build up my epsilon 2 that I needed in my expression here for g. We're going to need one more thing here. Also epsilon 3, which is 1, is certainly a specific positive number. And for that epsilon, since the limit of g is m, by definition there's a delta 3, such that if x minus c and absolute value is between 0 and delta 3, then g minus m is less than the epsilon 3, which is 1. Now in this case right here, as long as we pick x's that satisfy this inequality right here, then we have this inequality has true here. So what does this say? This says, well, let's look at what we can get out of that. Let's look at the absolute value of g. Well, the absolute value of g is the absolute value of g minus m plus m. So we're just adding 0 here. Now, we can use the triangle inequality and break this apart into two parts, the first part being g of x minus m and the second part being m. And so we can do the absolute value of both parts with the plus in between, and this gets a less than or equal to. That's our triangle inequality in action. But we know that the g of x minus m, according to this, is less than that epsilon, which was just 1, so this part's less than 1, so we get a strict less than here. So what do we get? We get g of x is less than 1 plus absolute value of m. Now we got three different deltas, so delta 1, delta 2, delta 3. We want all these conditions to be satisfied, so we pick our delta to be the minimum of delta 1, delta 2, and delta 3. So remember, we started with any epsilon up here, pick the delta that's the minimum of these three deltas, and suppose we get x minus c's less than delta, absolute value less than delta but greater than 0. Well, if this is true, since delta is less than delta 1, it's less than delta 2, and less than delta 3, we get all three of these concluding statements from above are true. Now, let's see if we can use these three pieces to assemble our limit, our inequalities that we need overall. Now, overall, what do we want to do? We're wanting to get f of x times g of x to have limit L times m, so this difference here needs to be small, less than epsilon. That's what we're looking for. Okay, well, let's look at this. What we're going to do here is we're going to add and subtract L times g of x. Of course, L minus L g of x plus L g of x is 0, so that's legal to do. Now, the reason we did this is we want to group this together into two terms and two terms. So we put these two terms together, and notice they both have a g of x. Eventually, we're going to factor out the g of x, and that gives us an f of x minus L. And put these two terms together, they both have an L. We can factor that, and we get a g of x minus m. So L times g of x is the right thing to stick in there to get this to work out. Now, the second step, we're actually grouping this 2 and 2, and then applying the triangle inequality. The absolute value of the first part, which is these two terms, plus the absolute value of these two terms has to be bigger than what we started with. So what we started with is less than or equal to this by the triangle inequality. Now what we do is we do our factoring, which is a distributive property factoring here and here. Here, the second one we factor out an L, the first one we factor out a G. Now we know a property of absolute value says the absolute value of A times B is absolute value of A times absolute value of B. So we can say this product, absolute value of this product, can be written as these two absolute values multiplied together, and same thing here. So that's actually, well, that's actually equal to what's up here, but less than or equal to is still accurate. Now, the f of x minus L, that's one of the things we're able to control and get it small. We can get it smaller than epsilon over 2 plus 1 absolute value of m. So we can replace that by that, and this becomes strict inequality. And similarly, the second inequality up here says the g of x minus m is less than epsilon over 2 times 1 plus absolute value of L. Now, let's see here. Absolute value of g, we know, is less than 1 plus absolute value of m. So we can replace that by that. And notice this 1 plus absolute value of m cancels, and that's actually equal to then just epsilon over 2 for that first term. On the other hand, we can put the second part and think of this absolute value of L over 1 plus absolute value of L. Remember, absolute value of L is a positive number. When you add 1 to it, you're going to get a number bigger than absolute value of L. So when you look at this fraction, L, absolute value of L over 1 plus absolute value of L, it's a positive number, top and the bottom, and the denominator is bigger than the numerator. So this is a fraction which is less than 1. So if I replace this by 1, then we're going to get a strict inequality here. Okay, so we get strictly less than epsilon plus epsilon over 2 plus epsilon over 2, which of course equals epsilon. So ultimately we started with this, and we see that it's less than epsilon, and that's what we want. And so by our choice of delta, for any epsilon we pick, if we choose the delta like we did above, then x's that are close within c of delta, then the f of x will be within epsilon of L minus m. So by definition of the limit of the product is the product of limits. It's a little tricky there. I certainly wouldn't expect you to come up with that on your own. That's a little bit of a trick. So you have to take a little bit of cleverness to work this out, exactly what to choose for these epsilon 1 and epsilon 2 and epsilon 3 up here. But as you can see, it does work out. We'll go on to do some more proofs in the next